Have you ever wondered what makes your phone, your computer, or even your ceiling fan work so flawlessly? Well, it's not magic. Tucked away inside pretty much every piece of electronics is a tiny but absolutely mighty component. Today, we're pulling back the curtain on the unsung hero of the circuit board, the capacitor.
So what in the world is a capacitor? Well, the easiest way to think about it is like a battery, because, it stores electric charge. But here's the real kicker, and you can see it right here. A battery, it's like a marathon runner. It stores a ton of energy and releases it nice and slow. A capacitor? It's a sprinter. It can't hold nearly as much energy, but man, it can charge up and release it all in a flash. And that speed, that's what makes it so incredibly useful.
To really wrap your head around how a capacitor works its magic, let's step away from all the wires and circuits for a second. We're going to use a really simple but powerful analogy, a water tank.
Okay, picture this. You've got water flowing through a pipe. If you suddenly slam a valve shut, the flow stops. Instantly, right? It's super abrupt, but what if we add a small holding tank to that pipe? Now the tank fills up with water. So when you close that main valve, the main supply is cut off, but the tank keeps the water flowing nice and steady until it's empty. It acts like a buffer. And that is precisely the job of a capacitor in a circuit. It acts just like that water tank, but for electricity. It stores up electrical energy. So if there's a tiny flicker or interruption in power, the capacitor just kicks in and discharges, smoothing out the supply and keeping everything running perfectly. It bridges the gaps. That's the key, ensuring a smooth, uninterrupted flow of power.
All right, the analogy is great, but what's actually happening inside this little component? Let's dive into the science and see how these things are built.
A basic capacitor is beautifully simple. It's really just two conductive metal plates, usually aluminum, facing each other. But here's the thing, they never, ever touch. And that's because in between them, there's a critical third piece, an insulating material called a dielectric.
This dielectric, this is the secret sauce. It's an insulator, which means electrons can't just flow right through it. But when you put it in an electric field, something really cool happens. It polarizes. All that means is its internal charges just shift around a little bit. This creates a barrier, and that barrier is the whole secret to how a capacitor stores energy.
So, how does it charge up? Well, when you connect a capacitor to something like a battery, that voltage starts pushing electrons onto one of the metal plates. They just start piling up, creating a negative charge. At the same time, the plate on the other side starts releasing its electrons. This whole process keeps going until the voltage across the capacitor's plates is the same as the battery's voltage.
Just think about magnets, right? Opposites attract. The exact same idea holds the charge in place here. All those negative electrons piled up on one plate are desperately pulled toward the now positive plate on the other side. But remember that dielectric, that insulator in the middle? It stops them from ever getting across.
And this tension, this separation of charges, creates what we call a potential difference, or to put it simply, a voltage. The capacitor is now holding on to stored energy, kind of like a compressed spring, just waiting for a path to let it all go.
Okay, so that's the science. But why does any of this matter? Let's take a look at where you actually find these little powerhouses out in the real world.
The short answer? They are everywhere. I mean, from the circuit board in your phone, which can have over 1,000 of them, to the motor that starts your ceiling fan or your air conditioner, even huge industrial buildings use massive banks of capacitors. They're truly fundamental to, everything.
Let's look at two of their biggest jobs. In large buildings, they're used for something called power factor correction. Now, that sounds super complicated, but it's basically just about making sure the electricity is used as efficiently as possible. It saves a ton of energy and money. On a smaller scale, a super common job is helping convert the AC power from your wall into the DC power your electronics need. The capacitor's job there is to smooth out that converted power, filling in all the little gaps to create a nice, steady DC supply, just like our water tank.
So we've seen how absolutely essential these things are. But what if you actually run into one? Let's do a quick practical guide. If you ever find yourself looking at a circuit board, here's what you need to know about reading and, more importantly, safely handling these things.
You're going to find two main values printed right on the side. The first one is its capacitance, which is measured in Farads, though you'll usually see it as microfarads. This just tells you how much charge you can store. The second value, and this one is absolutely crucial, is its voltage rating, measured in volts.
Now that voltage rating, it's not a suggestion. It's the absolute maximum the capacitor can safely handle. So let me ask you, what do you think happens if you ignore that number and apply too much voltage?
Yeah, the answer is not subtle. The insulating dielectric inside just gives up. It breaks down, creates a short circuit, and the capacitor will fail, often by literally exploding. This is a pretty dramatic way to learn why respecting component ratings is not optional.
So, the most important rule here, electricity is no joke, and capacitors can hold a dangerous charge even when they're completely disconnected. First step, always check for stored voltage with a multimeter. If there's a charge, you have to safely discharge it through a resistor. Never, ever touch the terminals until you've confirmed that the voltage is down to near zero.
So from smoothing out power to making timers work, the capacitor is this amazing silent workhorse. It's just a perfect example of a really elegant solution to a fundamental problem in electronics. So now that you know how this one tiny component helps run our entire digital world, it kind of makes you wonder, what other invisible technologies are hiding in plain sight?